Okay, in this video, I want to do some examples of separable differential equations and see what kind of wrinkles can come up and maybe take a look at the integral curves, kind of relating what we're going to do here in this um, video with things that we did in previous videos. Sorry, I can talk. I've just been in an all-day meeting, and so I'm a little bit incoherent, and you're just gonna have to deal with that, okay? All right. So yeah, separable equations example. So um, let's do a very simple example first. How about something like this? Dy dx equals y squared times 6 plus x. Here it is very evident that this is separable. I mean, it's written in the other order, but you can see here the idea. We've got a function of y only and a function of x only, and dy dx is being set equal to the product of these. Okay? So in this situation, we follow the prescription of the previous video. We separate the variables. We rewrite this as dy over y squared is equal to 6 plus x. And then we integrate each side, dx. Sorry, we integrate each side with respect to the respective variables. And symbolically, this works. But if you want the more rigorous justification, you think about u substitution and things like that, and you look at the previous video for how that was done. Okay, the antiderivative of 1 over y squared, remember that's y to the negative 2 power. So this is going to be negative y to the negative 1 power. An antiderivative, and I'll suppress the plus c, put it on the other side. Here, the antiderivative, or an antiderivative, is 6x plus 1 half x squared. Then we have our plus c. Now I'm going to solve explicitly for y. So if I do this, if I multiply both sides by negative 1, and then take the reciprocal, I get y is equal to what I'm going to write it like this: 1 over negative 1 half x squared minus 6x plus c. You might be wondering, why is it not minus c? Well, that's because minus c is the same thing as plus c, so I might as well just write plus c. Remember, c being a completely arbitrary additive constant. It doesn't matter if you take plus c or minus c, it's just the same. Okay. Yeah, so here I was able to write y explicitly in terms of x, and there it is. And you can check yourself. It'd be a lot of work, wouldn't it? But you can check yourself that if you were to replace this y here in y squared by this crazy expression here, and then take the derivative of that crazy expression, that, well, indeed, this would satisfy this differential equation. Okay? Easy peasy, right? The main technique is recognizing how this is written as a product of a function of x only and a function of y only, and then separating those variables. Let's do another example. Let's do an example of an initial value problem. How about? So let's take dy dx is equal to y tangent of x, okay? And let's set an initial condition where y of 0 is equal to 16. Okay, now what I'm going to do is separate variables. This is clearly a separable equation. The differential equation is. It's clearly separable. Maybe I should use colors here. And so I'm going to separate the variables and then integrate both sides. So I have dy equal over y, and over on this side I have tangent x dx, and then of course I'm going to integrate both sides of this. On this side I get the natural log of the absolute value of y. I'm going to suppress the plus c because I'm going to put it on the other side, and on this side I get the natural log of the absolute value of secant of x. Did I do that right? It's hard for me to remember. Oh, and plus c. It's hard for me to remember if I did that right, so I can check on the fly if I'm ever confused. Remember, the integral of tangent of x dx is equal to, this is review, the integral of sine of x over cosine x. dx, and then you use u substitution, where you let u equal cosine of x. Then du is equal to negative sine x dx, so that this integral becomes, when you write it in terms of u, negative integral of, so upstairs we have du, and downstairs we just have u. But this is negative natural log of the absolute value of u plus c. But u is cosine of x. But when you have something out here, a constant out here, you can move that into the exponent position by rules of logarithms. To the negative 1 power. But raising something to negative 1 power is the same thing as taking the reciprocal of it. So this is the same thing as the natural log of secant of x, or absolute value of secant of x. This is just review, okay? Just review. But this is how we get here. Okay, now the question is, how do we solve for y here? Well, I'm going to first begin by exponentiating both sides. So I get that the absolute value of y is equal to the absolute value. No, that's right. I'm sorry. That's right. Well, let me do it like this. E to the natural log of the absolute value of secant of x plus c. Then what I'm going to do is break this exponential up along this plus right here. Okay? Because I know that the exponential of a sum is the product of exponentials. So that tells me that I get e to the natural log of the absolute value of secant of x times e to the c power. Now remember, e to the c power is a positive quantity, as we've discussed. It's a positive quantity, and so we can see here that if we call that something new, let's just call, well, sorry, I'm going to rewrite that positive quantity as temporarily p. Can I do that? P stands for positive. Oh, and by the way, what is e to the natural log of something? That's just the absolute value of secant of x. Okay. But now, this is the absolute value of y. So p here is a, sorry, I should say p here is a stand-in for a positive constant. But this is the absolute value of y. That means y must be either plus or minus what we see here. So y is equal to plus or minus p times the absolute value of secant of x. So what this means is that we can replace this p here, make this equal to some number, let's call it q, which is non-zero. I'm just picking letters. Okay. It's non-zero because if p is positive, or an arbitrary positive number, then q plus or minus p is an arbitrary non-zero number, right? Now think for a second. What happens if p is 0? If p were to be 0, then that would make this function y equal to 0. And then you can go back to the original equation and ask yourself, is y equal to 0 a solution to this differential equation? And the answer is yes. In fact, you should have been yelling at me when I made my very first move here, because when I made my very first move here, I assumed, of course, that y was non-zero. So if y is non-zero, this whole calculation holds, but if it so happens that this constant, which we're calling q, is 0, we again get a solution. In other words, in the end, what we get is the following general solution, which is not a solution to the problem because I'm not done yet. We get y equals q times, let me not call it q, let me just call it c, okay? Q is the non-zero thing, c is an arbitrary constant, times the absolute value of secant of x. Okay? Now we want to employ, because I'm not done, this is the general solution to the differential equation. Now we want to employ the initial condition. The initial condition here is that y of 0 is 16. How do we use that? Here's how we use that. So 16 is equal to y of 0, but y of 0 is what we get by sticking 0 into the general solution. Secant of 0 is 1 over cosine of 0. Cosine of 0 is 1, and the absolute value of 1 is 1. So this is equal to c. In other words, the solution, the particular solution, is 16 absolute value of secant of x. Okay, that's it. Y equals 16. This is the solution which both satisfies the differential equation, but also satisfies the initial condition. Okay. Are there any questions about this? Cool. Oh, you can't ask questions. that was my classroom self. I was transported into the classroom just now, okay, in my mind. But of course, you can't ask questions because you understand that even though there are moving pixels which look like me right now, I'm not actually in front of you, and I cannot be responsive to the things that you're saying to the moving set of pixels. Okay, sorry. Let's move on. Here's another example of another problem. And I'm going to borrow these problems from a textbook by famous differential equations textbook, but I want to acknowledge that because I didn't make these problems up. Okay, here, let's do this one. I want to do two more problems, and I want to introduce something a little bit tricky about these. So let's look at this differential equation. dy dx equals x squared over 1 minus y squared. Did I say the book that this came from? This comes from the differential equations textbook by these two authors, Boyce and DePrima. And I remember taking this course when I was an undergraduate, and I learned differential equations from that textbook. So this is a very old textbook because I'm ancient, right? This would have been in the year 2000. No, not even 2000. 1997. Okay? Anyhow, this is a separable equation, right? Just to make that absolutely apparent to ourselves, I can rewrite this as x squared times 1 over 1 minus y squared, just by rules of fractions. So this is clearly separable. And so I'm going to bring to bear the usual techniques. What I'm going to have is the integral of dy over, now the reciprocal, I divide both sides by 1 over 1 minus y squared. And I get here, and so what I get here is, my bad, what I get here on the sort of y side of the Berlin Wall is 1 minus y squared dy. Those are my West Germans there. Sorry. Dude, none of you even, do you even know what I'm talking about? Right. I'm not, it's not like I'm nostalgic for those days or anything like that. Just, okay, leave me alone. And then on this side, we're going to have the integral of x squared dx. Yeah? Excellent. Now, let's integrate. So we get that y minus 1/3 y cubed is equal to 1/3 x cubed plus c. Right. And, yeah, well, cool. And so now what we want to try to do is rewrite this. But the problem here is, are we really going to be able to rewrite this thing where we solve for y? I think it's pretty tricky to solve this expression here for y, solve this equation for y. I think it's tricky. And the reason is because there's this cubic involved. Like, you can try stuff, like, you understand what I mean. Solving for y in terms of x, like being able to write y equals some stuff involving x only, no y's. I'm going to claim that that's pretty tricky business here. And in this kind of situation where you're dealing with this kind of tricky business, sometimes the best thing to do is to just leave your solution implicit. Write down an implicit solution for your for the solution to the differential equation, an implicit expression. So what I'm going to do is write down an equation which sort of isn't explicitly y in terms of x, only implicitly so. So what does that look like? It's going to look like me just moving over the negative 1/3 x cubed, maybe something like this, plus y minus 1/3 y. Oh, let me write it differently. Minus 1/3 x cubed plus y minus 1/3 y cubed equals c. Okay. And if I really wanted to, because c is the same thing as 3c, I could just multiply through by 3 and get x cubed plus negative x cubed plus 3y minus y cubed equals a constant c. And here is the expression for y implicitly as a function of x, okay? This doesn't explicitly give you y in terms of x. And let's just see why this kind of presentation is kind of necessary, right? Because if y you can write as a function of x only, then that function of x should pass the vertical line test. But let's just see what happens by taking a look at Desmos real quick. So I have Desmos queued up to show us something here. So look at Desmos. Look here. Do you see it? This is exactly the solution curves. And what I want to show you is what happens as I vary c, right? So as you vary c, you can see that very interesting behavior happens to the solution curves. These are what we've been calling integral curves, right? These are basically just graphs of the solutions, or not graphs. It's not the right word to say, but the curves corresponding to solutions to the differential equation. You see I have really interesting, strange behavior around certain critical values. Like look at that at -2. Huh. And yeah, nice and smooth there, but some really strange behavior right around there. Anyway, if we lock in, let's say, on this particular weird curve, the thing I want you to notice is that this is not the graph of a function, right? So we can't really write it as y equals some function of x. Does that make sense? It's just not doable unless we restrict ourselves to certain values of x and y. I mean, like, if you take, I don't know if I can draw here. I can't draw on this thing. But if you take this part here, which goes just around to here and then stop, maybe you could write y explicitly as a function of x, right? And then you could write this portion right here, because those are portions of the curve which pass the vertical line test, right? Which could be written as functions, graphs of functions of x, okay? But the general solution, the full-blown curve, can't. So we're not going to do any better than what we have here. We're not going to do any better than that. So that's why we stopped there. One more example of this sort of phenomenon, which I want to show you, and then we'll call it a video. This one's a little bit long, but that's okay. And again, this is taken from good old Boyce and DePrima. Yeah, it's this one here. Okay. Dy dx equals 4x minus x cubed divided by 4 plus y cubed. Alrighty. And here we're going to take a, well, let's just solve this. I won't worry about initial conditions because I am kind of interested to see what happens to the family of solutions for this particular differential equation. So we're going to do the usual separation of variables thing because this is a separable equation. I hope you can all sort of identify that with your brain balls. And then we are going to multiply both sides by 4 plus y cubed and move the dx over to the other side typographically and get and then integrate to get the integral of 4 plus y cubed dy is equal to the integral of 4x minus x cubed dx. What could be simpler, right? Now integrate. 4y plus 1/4 y fourth is equal to, what is the antiderivative of that? That's going to be 2x squared minus 1/4 x to the 4th plus c. Okay? And then we could play the same game of like moving stuff over and rating everything in terms of c only, and then maybe like normalizing some of these constants. I don't know. This is a pretty good solution, but the point that I really want to make is that you're going to have a real tough time solving for this in terms of solving for this explicitly in terms of solving this thing explicitly where y is a function of x. I'm borderline incoherent because I've been in a stupid meeting all day, okay? So instead what we're going to do is just leave this as an implicit expression relating x and y together. And if we do that, I mean, we can take this, but maybe if we want to write it kind of in the format that we did earlier, we have 1/4 y to the 4th plus 4y, and I'll add, subtract 2x squared and add 1/4 x to the 4th. And then this is equal to our constant c, and maybe I'll just multiply through by 4 to clear out some of these annoying fractions. So I get y to the 4th plus 16y minus 8x squared plus x to the 4th is equal to c. Let's look at what these curves look like, because it's it's always interesting to see, and I think I graphed them here. Yeah, for varying values of c. So you get this truly strange closed curve here for this example. And if you let c run between negative 25 and 25, you can make an animation, which is what I've done here. And hopefully, well, you can see what's happening. Oh, interesting. There's this very interesting moment where this blob like pinches off into two smaller blobs, right? Very interesting. Anyway, so this is what implicit solutions kind of look like. In particular, please acknowledge this you can't really write as y equals a function of x, not this whole curve. You might be able to write down portions of the curve. In fact, you could, but not the whole curve all at once. And this is the reason why we have implicit solutions, right? Okay, that's enough for this video. It's gone on long enough, and want to do one more.